Hello, I'm E.Tarte, math teacher. This is another in my series of solution videos to some of my math challenges. The math challenge for this solution video is my sum of square numbers challenge. In that challenge, I presented a table of square numbers. This table goes from 1 squared to 9 squared. The square numbers are in the right-hand column. Each is gotten by multiplying the number in the left-hand column by itself. And the challenge was find 3 consecutive square numbers that add up to 6,160,469. And I also asked that you work it out without a calculator. Here's my solution. I write an algebra equation based on the challenge. The 3 consecutive square roots will be n minus 1, n, and n plus 1. The 3 consecutive square numbers will be n minus 1 squared, n squared, and n plus 1 squared. And based on the challenge, those 3 square numbers add up to 6,160,469. I multiply out the n minus 1 squared and also the n plus 1 squared, and I get this new equation, n squared minus 2n plus 1 plus n squared plus 2n plus 1 equals 6,160,469. I simplify the left side of the equation. The minus 2n and the plus 2n add up to 0, so they disappear. I have 3n squared plus 2 equals 6,160,469. I subtract 2 from both sides of the equation, then divide both sides by 3, and I get n squared equals 2,053,489. That should be the middle of the 3 square numbers that add up as required. It should definitely be a square number. I'm now going to verify that this number 2,053,489 actually is a square number by finding its square root using the method that I developed in an earlier math video that I recommended in this one to be watched before watching this one. Using that method to find the square root of this number, I split it up into groups of 2 numerals starting at the right and moving to the left, and as it turns out there's only 1 numeral at the extreme left. 1 squared is 1, 2 squared is 4, that's too much. 1 squared is 1, 2 minus 1 is 1, and I bring down the next group, 0, 5. I double the 1, that's 2. This is going to be 20 something, and I must put the same numeral here and here. That numeral will be 4. 4 here making 24, and 4 up here. 24 times 4 is 96. 105 minus 96 is 9. I bring down the next group of 2 numerals, 3, 4. I will now go through that process again. I double the 14, that's 28. This will be 280 something. I must put the same numeral here and here. The correct numeral is 3 both places. 283 times 3 is 849. I subtract and get 85, and I bring down the final group of 2 numerals, 8, 9. And now that process once more. 143 doubled is 286. This will be 2,860 something. I must put the same numeral here and here. The correct numeral is again 3 both places. 2,863 times 3 is 8,589. And so, by that square root method that I developed in that other video, 2,053,489 is a perfect square. Its square root is 1,433. So here is that entry put into the x squared table. There's the 1433, right above it 1432, right below it 1434. Now we need to get the other two square numbers, the one here and the one here, so we'll have all three of them. Well, it's a fact from an earlier video that I recommended that we have addition facts in the x squared table. For example, 9 plus 3 plus 4 equals 16. Another example further on, 36 plus 6 plus 7 equals 49. And that phenomenon is true throughout the table. And we can use that fact to find the other two square numbers that we need. I can take the sum of 1432 and 1433 and subtract them from this middle square number to get the one before it. That one turns out to be 2,050,624. And I can add 1433 and 1434 and add that sum to the middle one to get the one below it. That one turns out to be 2,056,356. We can verify that each of these is a square number and that they are indeed the squares of 1432 and 1434. We can do that by a calculator or by squaring these numbers by hand, or taking the square roots of these numbers using that square root method. So here in the right-hand column are the three square numbers that I asked for, the three consecutive square numbers that add up to 6,160,469. So that is my solution to my sum of square numbers challenge. Thank you for watching this solution video.